Now, our next speaker is Tomaž Prosen from Ljubljana. He is known from his very important works about integrable systems, about non-local charges, and so on. Now he will speak about integrable deterministic dynamics in this context, please.
Thank you. Hello. So, yeah. So first, I would like to thank the organizer for inviting me to this beautiful place. Also, I would like to thank Springer for financial support. And as you see, my title is a bit long, but I hope I'm not going to distract you with this long title. So, I'm sorry. So this is basically the menu for my talk and also the main heroes responsible. Do you see well enough? I mean, I don't see very good contrast, but it's okay. From this side, maybe it's not so good. So, and my voice is okay, or yeah. So these are the heroes from my, I'll tell you about the story of a surprise. And it's about appearance of Kada-Parisi-Jank universality in quantum spin transport, which nobody expected, at least we didn't expect it. And also the community was quite surprised. And the problem is still not resolved. So basically, I'm telling you about evidence we have for this kind of manifestation of Kada-Parisi-Jank equation in quantum physics, or at least in physics of integrable systems. It's not, as you will see, even though it was discovered in quantum spin transport, it seems that what is important is integrability and non-abelian symmetry. And this will be the first half of my talk. So we'll try to give you evidence for that, even experimental evidence, but mostly numerical evidence, and some heuristic ideas why we think this should be the case. But it's still not clear why, this really belongs to Kada-Parisi-Jank or KPZ universality class, even though it's not even clear whether it really belongs to KPZ. What we will see, I want to try to convince you that the 2-point functions satisfy KPZ universality, and maybe fluctuations are going beyond or are in different universality class. So the second part of my talk will be about what I call anomalous fluctuations or critical fluctuations. This is the second part of my title. And this is, I would immediately try to make connection to Marton's talk yesterday, where he showed you that the scaled cumulants, that the cumulants scale with different exponents, which is different from what people find from large deviation theory, where the cumulants scale with the same, like they are all 1/t or 1/t to the alpha with some exponent, which is universal for all cumulants. So this is something that goes beyond, let's say, the standard paradigm of large deviations. And we'll try to kind of argue that this is maybe interesting, and it's again generic for this type of integrable systems with non-abelian symmetries. Maybe not even non-abelian symmetries are needed for that. So the third part of my talk will be about, because the first two, let's say, chapters will be simply throwing to you some numerical evidence, which is at least puzzling. But the third part will be about analytical solvable model, with which we can explain a little bit of that observations, let's say at least about critical fluctuations. So there'll be a model of exactly solvable model of full counting statistics, which will have these features of integrability. So, and it will be it will be deterministic. I mean, the idea which I would try to emphasize here is that I'm treating deterministic models. So, I mean, this is something that, is different from what people usually do when they consider KPZ. They look at stochastic models. Now here we're trying to look at emergence of KPZ in deterministic models. So let me start with the first observation, or at least, the first observation which kind of found some impact, let's say. I mean, I will show you that there are previous results really suggesting the same phenomenology, but this was the first one which really was kind of very clear. This was the study we did 2017 with Marco, the two Marcos, Marco Žindarić, the senior Marco, and the PhD student Marco Ljubotina. And we looked at a very simple protocol, which is known as inhomogeneous quench protocol. So basically the idea is to connect two pieces of two semi-infinite pieces of a spin chain. So we treated this simple model, which is the Heisenberg spin 1/2 chain. Not sure if I can navigate well, but this is the Hamiltonian, which most of you know very well. It's one of the paradigmatic models of many-body physics, also statistical mechanics, quantum statistical mechanics. And we started from an infinite temperature state, but with slight magnetic bias. So the idea is to look at spin transport at high temperatures. So everything is at high temperature, but the idea is to make bias in magnetization. So the idea was, okay, let's take, unlike most of other studies where people look at low temperature transport, where they would start from a domain wall state, right? This is not a domain wall state. This is a, let's say, a partly magnetized domain wall. So you take a small parameter mu. Mu is a small number for us, not right. If mu is a 1, this would be the domain wall, right? 2 ferromagnets. But now this is just 2 density matrices of 2 semi-infinite spin chains, slightly magnetized. And then you look at what happens. And in the limit of mu going to 0, basically the observable, the spin density and the spin current. This is spin density, this is spin current. Space-time plot, let's say a heat map plot of spin density, spin current. And this is a space, this is time. And you see that you have this kind of diffusive, if you want. This is diffusive. This is delta equal to 1.5, and this is delta equal to 1. So you see, this would be x squared. This would be, x is equal to, x squared is equal to t. So the typical diffusive pattern, diffusive envelope. But this would be x is equal to t to the 2/3. So it is having it's broader than the usual parabola, and this would be the corresponding density plots of the current correlation function. So I mean, what I'm saying now is this is equivalent to correlation functions, 2-point correlation functions. So either you look at because if mu is small, you can basically take perturbative expansion in small mu, and you find, well, we have some echoes. So and then you find that I mean, this, like, let's say single point observables starting from inhomogeneous initial state, which is non-equilibrium, are equal to 2-point correlation functions at equilibrium at infinite temperature of local spin density. Okay, so now this was just a warm-up numerics, which was then we could analyze more in detail. Of course, I mean, this is kind of very difficult. This type of numerics, for anyone who has tried this, I mean, you know that, I'm just going back a slide for a moment. This is very difficult because, you know, these are interacting many-body quantum systems, so there is no way to simulate this exactly. So one has to resort to some approximate methods. The method we used here was DMRG/TEPD, so time-dependent density matrix renormalization group method, which has all the caveats that some of you who do this for living know very well. I mean, these methods have problem because entanglement grows, so you cannot trust them. You can only trust them for a finite amount of time. So you see here we went to times which are of the order of a few hundred. The question is, I mean, can we trust them? Of course, you do that by just increasing the so-called bond dimension, the tracation dimension, and then you compare the results and you hope for the best. So, and I will just tell you later that other people have confirmed this with, let's say, much better computers than what we have in Ljubljana, but still, you have to take this with a grain of salt because it's approximate numerics. Yeah, but then later we will show you that you can do basically quasi-exact numerics with different models which predict exactly the same sort of physics. So just to tell you now what we analyzed in more detail. So now you can analyze the dynamical exponents. So how does the integrated charge across the center, across the cut, grow with time? Now for the isotropic case, it grows with exponent which is very close to 2/3. For isotropic, for easy axis case, which is diffusive, which might be diffusive based on this numerics, the dynamical exponent is alpha is equal to 1/2, or z, which is 1/alpha, dynamical exponent would be 2. So then this suggests the following phase diagram that for delta less than 1, I will not discuss this in my talk, but this was the chairman mentioned some results which I did in several years before, which basically concerned this regime. These quasi-local conserved charges basically were used to show that this regime for easy plane regime of XXZ model is really ballistic. So dynamic exponent is equal to 1. Now we have evidence that this is diffusive for delta larger than 1 and delta equal to 1, which is isotropic, which has additional non-abelian symmetry. Isotropic Heisenberg model has dynamic exponent 3/2. So this suggests this already suggests some puzzling similarity to KPZ physics, but it was not clear until the next paper 2 years after, where we try to just, now then we become more brave, right? We kind of, there was some response from the community. People have understood. I will show you later the references, but at least within GHD picture, people were able to explain this 3/2, so we were more courageous. We pushed our computers even more. And there was another trick, which I don't have time to explain, but there is the trick of integrable tortorization, which means you can make time discrete, and you can run your revolution in time steps equal to 1, which means you gain a factor of 20, or I don't know what is your favorite Trotter-Suzuki split step method, but you can do much faster because time step is equal to 1. And then you compute scaling function, that is the spin density if you want, or density correlation function, or current correlation functions. The two profiles are in the top and bottom plots, and you can compare them to Gaussians. I mean, if this was a normal diffusion, then you would expect that profiles are Gaussian. Of course, they have to scale with different exponent. So here what you plot is x, or in this case r, the distance. This is the correlation function, so it's the distance r divided by t to the 2/3. So you scale with the correct, let's say with expected 3/2 dynamical exponent, and then you expect that you get some profiles which are close to Gaussian, but they're not quite Gaussian. So you know, these green curves are Gaussians, but now what you get is data which is following, you know, some curves which are actually turned out to be exactly the scaling curves which were found for KPZ universality class. This data has been taken from famous Prachofer-Spohn paper, which was analytical results, well, tabulated scaling functions for the so-called polynuclear growth model, which is in KPZ universality class. So this is an evidence that 2-point functions now are really very well described, up to, let's say, 3, 4, if you are brave, even more orders of magnitude, and they are following what people have expected or found for KPZ universality. So now, okay, just some dictionary, right? So now you become really, I mean, you try to understand what's going on. So now you compare to what people have found for KPZ universality. You define the KPZ 2-point function or correlation function. Now I don't have time to go into these definitions because I imagine my talk should not be too technical. So I ask you for some patience here. I mean, if anyone is interested, we can discuss this later on the trip. But the idea is now, okay, I mean, this is, as I say, this is an open problem. So we don't really understand. What we have now is basically a dictionary saying that let's compare with KPZ if we take the gradient of height field identifying with the z component of the spin. So one component of the spin. Now this is isotropic Heisenberg model. It doesn't matter which component you like. Let's take z component. And then what it turns out that basically what you get is KPZ correlation functions if we identify the gradient of the height field with the z component of the spin. Okay. And then there was a lot of follow-up studies which suggested that this goes, I don't know, beyond quantum paradigm. It goes beyond SU2 paradigm. There were people from more serious, let's say, numerical groups like this group from Germany, around Schmidt-Eckert and Evers, who have used now their supercomputers and bond dimensions of order of 2000 to show that our results make sense. And then there was, again, as I said, there was people who checked classical models like this group from India, and myself with my student Žiga Krajnik. And then I think the most remarkable study was the one, well, there was these two studies, which I will point out later. But I should also apologize for anyone who doesn't find himself here on this list, because this is by far incomplete list. I mean, there are now tens of references which address this problem and confirm this sort of phenomenology. So, but what I want to stress is there are two papers which I want to point out in particular, because there are papers who explained why there should be 3/2 dynamical exponents. I mean, first there was this paper which came out soon after our work in Nature Communications by Sarang and Romain, who used kinetic picture of GHD and giant quasi-particles. The particular anomaly in which the mobility of quasi-particle decreases with growing, let's say, mass or extent of quasi-particle, to show that 3/2 is the only kind of self-consistent exponent which is possible for this spin transport. And then there was this PRX paper last year, which was basically by the same people, extended by Ene and Jacopo and Wright and Ware, who basically generalized this to arbitrary integrable theory with nonabelian symmetry. That's why the buzzword superuniversality of superdiffusion, where they found that, again, the only self-consistent allowed exponent is 3/2. So this is I mean, suggesting there is something very, very robust and very general going on, that basically, yeah. But then, you know, you still don't know whether you should have KPZ, right? I mean, first there is dynamic exponent, then there is the whole scaling functions. And then there are works among those, also other works. But there was actually a very interesting paper just a few weeks ago coming out the archive. I didn't manage to quote it yet, but by Norman Yao and collaborators, where they simulated SU3 invariant spin chain, integrable spin chains, and they again found that they have the same scaling functions of KPZ or Prachow-Verschpon scaling functions. Okay, now the exciting thing is that now there are experiments actually which confirm this phenomenology. There are two groups of experiments. The first is the, let's say, the cold atom quantum simulators. There is a paper from last year of Emmanuel Bloch's group, which found dynamic exponent 3/2 in Heisenberg in a quantum simulation of a Heisenberg spin chain by direct counting of atoms, transported atoms. I mean, they prepared the non-equilibrium state the way that we suggested, bipartitioned two-density state around half filling. And then they counted number of atoms transported in time t, and they found this is basically a quasi 1D system. So there is there are basically two dimensions, but there is coupling along one dimension, which is potentially much larger than coupling along the other direction. So they can simulate. Sorry, they can simulate. They can measure actually the exponents from 1D to 2D, and they found that. And then, of course, there is some tunable. I mean, this is the parameter with which they break equilibrium. So they go to non-equilibrium quench, and they find that you have in 1D, you have well, this is the parameter which, yeah, they have to go to zero half filling state, that is net magnetization equal to 0. To get 3/2 in one dimension, and in two dimensions they get 2, which is consistent with normal diffusion. So this is very nice to see that, you know, this strange observation actually can happen in the lab. I mean, the results are consistent with what people see in the lab. Even more reassuring is to see this other experiment. Sorry, okay. There is this other experiment from Oak Ridge, from Alan Tennant's group, which is really the experiment in solid state using neutron scattering. I mean, the old fashioned solid state experiment of dynamical spin structure factor. Sorry, this is not very nice reproduction. On my computer, it looks much nicer, but anyway, it's just a copy of PDF from the paper. So what they have shown is that, of course, this is a very dirty experiment, so we shouldn't expect too much, but what one can show, one can convince, is that if you look at dynamical structure factor, the way this diverges with Q, the momentum, around Q equal to 0, if dynamic exponent is 3/2, so it should also diverge as Q to the minus 3/2. So the fact that what people find around, actually this is around room temperature, they find exponents which is with 0.1. I mean, this is best fitting exponents. This is numerics. They do for comparison. This is a real experiment, and exponents are something between 0.56, 0.35, and so on. So one could say these are very close, using experimental errors. They are very close to 1.5. Okay, now let me go. How am I doing with time so that I don't? Okay, good, great. So now I will just go for 5 minutes. I mean, I try to be, you know, pedagogical and illustrative and not going into technicalities in my talk, because I understand this is a very broad audience. So for those who are kind of not willing to digest some formalism, maybe they should fall asleep for 5 minutes. I'll just present a very nice model within which this phenomenology can be nicely illustrated. Let's say we don't actually still prove anything, but it's a kind of a class of minimal models for which we find this super universal Carrère-Parigi-Zank universality behavior of spin transport. There's a model which we call integrable matrix models in discrete spacetime, and I will just show you the couple of technical slides with definition of the model and how, and then I will go to some numerics and later to some other results which I promised in my initial overview. So, but this model is so simple that I can explain it in 5 minutes, I guess, at least for people who have some inclination towards cute little simple models. This model has, it's defined on a space-time lattice. So it's a many-body model, but it's a classical model. And actually, it turns out this model is just a kind of mean field limit of quantum spin chains for SUN symmetry. So it's really the, or if you want, it's the classical limit of SUN. It's the integrable classical limit of integrable quantum SUN spin chains, but those are very hard to simulate. And these are classical limits that are much easier to simulate. And the phenomenology, which we will find, I immediately announced this, is exactly the same. So maybe it's easier to understand these models, but I'm just describing the models and why they are integrable and why they are so easy. So these models are defined on discrete, on compact phase space. I will describe in the next slide what I mean by that, but imagine now the phase space is just phase space of matrices. So it's first of all, you define a two-matrix map which maps a pair of matrices to a pair of matrices, and it does it in a very simple way. It swaps the matrices and then it conjugates them with a sum of matrices plus some complex parameter, I times tau, where tau is real. It turns out that this map has several cute properties. The map has these properties that it preserves the hermiticity and square one of the matrix. So if the matrix squares to 1, also the image matrix squares to 1. The inverse map is just a map of negative time. So this tau will be interpreted as a time step. It, as I said, conserves hermiticity and conserves the sum of the spins or the sum of matrices. So this is like SUN spin conservation, as you will see. Okay. So, and what is the phase space? Well, the phase space is what is known in mathematics or mathematical physics as complex Grassmannian. So basically, it's a phase space of all projectors of certain rank, Hermitian projectors or self-adjoint projectors of certain rank of n by n or n-dimensional complex vector space. So, I mean, you can just identify these projectors by just subtracting certain. I mean, this matrix is square to 1, but you can write a matrix 2n minus 1, which will be a projector, right? Because these matrices will have eigenvalue or m whatever. I mean, these matrices have eigenvalues plus 1 or minus 1, but you could map them to matrices which have eigenvalues 0 and 1, which will be just projectors. So anyway, these matrices can be parametrized by matrices which are SUN rotations times conjugating this what we call a signature matrix, which has eigenvalues plus 1 and minus 1. So K is the rank of this matrix. So if you add identity or if you subtract this, well, I mean, you could easily imagine, I mean, you could subtract this from identity, then you get rank K exactly, right? Yeah. But anyway, so it turns out that this, this matrices from this space are preserved under this mapping, right? So now you can understand the phase space. What is the dimensionality? This phase space is just a quotient space. It's a symmetric space. It's a quotient space of UN over U of K cross U of N minus K. And its dimensionality is even. So it's like a sphere for N equal to 2 and K equal to 1 is just a 2 sphere. Otherwise, it's an even dimensional symmetric compact space. So our dynamical system now is defined over tensor product of N copies of this space or direct product, Cartesian product of N copies of such space. And you can define dynamics, you can define dynamics now like you do dynamics of quantum systems by a circuit. Now this would be a classical circuit. You have N matrices, like in this case 6 matrices. You apply this map in terms of mapping the pairs, 2 pairs, 1 pair, 2nd pair, 3rd pair, and then you shift the matrices like in these brickwork quantum circuits, you take another image and then another half-time slice and so on. So you repeat. So this will be the dynamics. Right? This will be like a space-time fabric of this 1 + 1 dimensional discrete space-time matrix dynamics. Yeah. And then, you know, what is nice about this is that these dynamics can be derived from a zero curvature condition. I will not go into detail because, as I promised, this will not be a technical talk. So I'll just give you a snapshot. But there is a simple way to understand this dynamical map as a zero curvature condition for this discrete parallel transport along this square, right? So there are two Lax operators which are very simple. They are kind of minimal, if you want. They are really linear in everything, and dynamical map can be just understood as consistency condition for the fact that this transport is identical to that transport, and then it gives us this map. Yeah. So as I say, I will have to be fast, but you know, and then you can define other concepts from integrability like monogamy matrix and transfer matrix. This is a classical system. So the transfer matrix is in fact not a matrix, but a function of classical phase space variables. But you can define it. You can define a product of Lax operators. You can define the trace of that, which is the phase space function, not a transfer matrix, but phase space function. It's a function of the n-tuple of matrices and a spectral parameter, which is a complex parameter. Just note this staggering of spectral parameters, lambda, lambda plus tau, lambda, lambda plus tau. So tau is the time step. So for those who have some mileage in algebraic beta ansatz, this is very similar to ABA, but it's classical. So it's a bit of, you know, when you are in discrete time, it looks more like ABA than when you take continuous time, right? But, you know, it's we don't actually use this for anything except for confirming that this model is integrable, because we can't use it for anything else. We are not able to use it for anything else. Okay, so now this is just a statement of integrability, sorry. Again, statement of integrability would mean that now this set of transfer maps are conserved in time, so under composition with the map, they don't change for any value of spectral parameter, and they are commuting in the sense that the Poisson brackets among themselves for arbitrary parameters are vanishing. But then you can define the conserved charges. The conserved charges again go under the standard recipe as logarithmic derivatives of the transfer map, which are again local or phase space functions, which are sums of local charges. Now, locality, we could now spend another 30 minutes to discuss locality of these objects, which would be very interesting, but I have no time, so I skip it. But these objects are not always local. They can be shown to be local only for symmetric spaces with rank 1. For symmetric spaces, this K with ranks which is not equal to 1 or n-1, these objects might not be local, but I suspect they would be quasi-local, but we have not looked into that. Okay, now there are continuous limits. First, there are continuous time limits, which gives us the Hamiltonian system with a lattice Landau-Lifshitz Hamiltonian. This would be a generalized Landau-Lifshitz Hamiltonian. Now, for n equal to 2 and k equal to 1, would reduce exactly to Landau-Lifshitz. Sorry. Now, you can take continuous space as well. You get SUN Landau-Lifshitz field theory. So this is just to tell you that this goes back to physics. If you do the appropriate limits, I mean, it becomes more physics-like looking models. But again, I think it's just as well physicsy as the continuum models. For example, in n equal to 1, 2, k equal to 1, this is the SU2 symmetric model. Then it becomes exactly what people know as Landau-Lifshitz or discrete lattice Landau-Lifshitz model with this logarithmic interaction. Yeah. But now, before you go do the continuum limit, you get this interesting two vector map. Again, it's a rational map of two vectors to two vectors, which has manifest SO3 or SU2 symmetry, if you want. Okay, now let's see how the correlation functions look like. So now I stop with, let's say I stop with mathematical physics. Let's go back to brutal numerical computations because we can't do anything else. So let's compute correlation functions of nodal charges. Now we have these SUN models. So now the role of SZ now becomes just an arbitrary nodal charge or component of the nodal charge. And take any of those for this SU2. This would now be SU3, K1, SU4, K1, SU4, K2, SU5, K2, 1, SU5, K2, and so on. I mean, you see this in the caption, but doesn't really matter. The point is that all these correlation functions are the same. These are spin-spin correlation functions, space-time plots. And if you just look at how they decay at x equal to 0, they decay with a dynamical exponent, which is marvelously close to 3/2. So just to confirm, this is 10 minutes. Thanks. So now this is just to confirm that this is the simplest model you can generate on a computer. This is like 1 or 2 days of CPU time on your laptop. And it gives you the dynamical exponents and the scaling functions, which agree marvelously nicely with what you expect for KPZ. These are deterministic systems, no noise. These are integrable systems, very much unlike typical models like TASEP, which are in KPZ universality class. Well, I should bite my tongue now. TASEP has linked to integrability, but it goes on different level. So, yeah, imagine polynuclear ghost model, for example, and so on. Okay, now again, this is scaling functions for these models. Again, you see that they have nicely matched. They are not Gaussian. The red curves are Gaussians, but they are very close to Prachhofer-Spohn, which is this black dashed line, which is going in the middle of the numerical data. Okay, now I think to move on a bit faster. So there is some magnetic field, which I will not discuss, but now let's go to fluctuations. So now the next question we ask is, what about fluctuations? Now this would be like 2-point functions. This would be like variances of observables, how they grow with time. And diffusion predicts dynamical exponent 2. KPZ predicts 3/2. But what about fluctuations? Sorry. So now we go now to a simpler model, because until a few last minutes before end of my talk, I will still consider just numerical simulations. So now let's go to the simplest variant of this model, n equal to 2, but consider also its anisotropic deformation. This has been a paper together with Vincent Pasquier and 3 guys from our group, published last year. It's basically the idea of that paper is, let's take this cute map. Oops. Let's take this cute map here, and let's try to find if there is a Q deformation of that. So this is a rational functions, but let's try to find Q deformation of that, which would be corresponding to XXZ, would be like a classical limit of the XXZ chain. And indeed, Vincent helped us to show how we can do that. I will not show you any detail. I will just show you what happens now if you do numerical simulations of 2-point functions. So now what we are doing now is just looking at equilibrium. And there's one thing which I forgot to stress. Whatever I showed you now is equilibrium physics. That's another reason why you should raise your eyebrows. I'm telling you about emergence of KPZ universality in equilibrium physics. I mean, this is something that is against the common wisdom, because KPZ is supposed to be something which models far from equilibrium phenomena, right? Now we are basically finding some far from equilibrium duality. I mean, we are at equilibrium. Our states are equilibrium states which satisfy KMS conditions, if you want, and so on. So now, starting from equilibrium state, we now look at fluctuations in equilibrium, right? And what do we expect for those? We look at integrated current, picking some point, x equal to 0. Doesn't matter which, because the state is translation invariant, and integrate the local current. So we basically integrate the total charge, the total Nodal charge, which is transported through some imaginary point in finite time t. And then we look at the fluctuations of that object, and this fluctuations defines for us dynamical exponent. So that's how we define dynamical exponent, as a connected 2-point functions, or the variance. But then we look at higher moments, higher cumulants, and we ask ourselves how to or the distribution of the scale transport information, right? The whole distribution. So we define the scale current, which we divide by the square root of the variance, and then we look at this its cumulants of the scale current. So this means that if these cumulants are non-zero, the distribution of scaled cumulants, the scale current, is non-Gaussian. And this is something which should already be surprising if you find non-Gaussian. So what do we find? I think I should close fast, so I'll just show you some slides. This is what we find. We find this is for easy axis, so easy plane. Sorry, this is would be delta less than 1, easy plane. XXZ, classical XXZ. This would be isotropic. This would be easy axis, so delta larger than 1. You should again raise your eyebrows by seeing this, because we said this is normal diffusion. Yeah. Sorry. So you see, I mean, this should be surprising again, because I said to you, this is normal diffusion z equal to 2, but now the tails are completely off the Gaussian. So this is integrable system, which appears to be diffusive when you look at up to 2-point function. But if you look at high point functions is totally non-Gaussian. So we should understand that. Yeah. And then there is, just to compare for the sanity of mind, this is a non-integrable deformation. So we break integrability. I don't tell you how because there is no time and it's not essential, but we break integrability and we find perfectly Gaussian fluctuations. So just to check for ourselves that we're not doing something meaningless. Yeah. So now, okay, now you can ask, is this Gaussian? It looks like it, right? But now, yeah, okay, we'll discuss this later. But now let's look at this guy. This guy now has now we are looking at the fourth cumulant as a function of time. And curiously enough, we see the logarithmic growth of the fourth cumulant, meaning that this distribution has not converged at the times of simulation, but it builds fat tails. It builds fat tails, which means, thank you, which means that, you know, even fourth cumulant might not exist at infinite time limit. Okay, this is just to, you know, to raise your curiosity. We don't explain these results. We just show them. I mean, now we are working on much more detailed numerical simulations. We are running our local clusters for weeks already, but you know, I cannot still report you new results. But basically, we still find anomalies. Now, why should you be surprised? Because now there is this story that also began in this community around KPZ by Herbert Spohn and Christian Mendel. Well, I mean, Herbert Spohn was basically responsible for this idea of using KPZ, well, using what he calls nonlinear fluctuating hydrodynamics, right? And you know, which can reproduce KPZ physics at some instances. And so he proposed that one can use this also to model deterministic systems like anharmonic oscillators, but which are though non-integrable. So it's just to show you that in non-integrable systems, which are though deterministic without external noise, they are self-generating their own noise. You can find something which is within KP0 universality class. So for example, this is the 2-point function. This is the three peaks of the 2-point function with 3 conserved charges. Usually these objects have still conserved charges like conserved mass, conserved momentum, and conserved energy. So there correspondingly, there are 3 peaks in correlation functions. The central peak, this is what we are seeing, what we are looking at here now. The central peak is Gaussian. So they find Gaussian, but then they find 2 additional peaks, the so-called sound peaks. And for those, they find KPZ physics, KPZ, that is 3/2 dynamic exponent. But this is the fluctuations, the probability distribution of the integrated current. For this, they find what people would expect in the corresponding KPZ universality, the so-called Baker-Rains distribution. So this is all kind of what, I mean, people could explain because this is an old story. Well, old, I mean, like of the order of almost 10 years old. But here we don't see that. I think I should probably soon close. So I should probably just stress a couple of points and then leave the rest for anyone who's curious to discuss over the excursion or the breaks. But anyway, so where am I now? Now I'm a bit confused. Okay, so there are a couple of things, and with one thing I would like to return to the last point of the talk of Martin yesterday. I mean, the idea is, can we reproduce scaled cumulants from large deviation principle? That is defining large scaled cumulant generating function. The idea is looks very innocent. Indeed, we can define this f of lambda, which is the limit t to infinity of log moment generating function divided by the appropriate power of t. And this power is defined by the dynamic exponent. The problem is that this guy does not generate scaled cumulants, because if it did, these scaled cumulants would all decay with the same, all grow with the same power of t, but they don't. Again, I have to hurry up, so I don't have time for details. But this is what you see, for example, even in the isotropic case, this would be for isotropic case, the scaled cumulants, I mean, the cumulants, not scaled cumulants, but cumulants grow with different exponents. Fourth cumulant doesn't even grow here at this until this time scale, but the sixth cumulant beautifully grows with the power law exponent. Okay, so it's a kind of critical. That's why I like to think of it as the critical fluctuations, because scaled cumulants don't converge, but they still diverge with different critical exponents, with different exponents in time. It's details to be understood, but I will close it now. I have to close it, so I have to kill a couple of slides. But I will just close with these two slides, this one and the next one, just to give you some advertisement that indeed something can be understood, because you might think, okay, this is all numerics, you know, we are all confused and probably there's something wrong. So at least this critical scaling of cumulants can be nicely reconfirmed in this exactly solvable model, which is what we call, well, this model doesn't have any nice name, even though it's a nice model. Basically, it's very similar to hardcore, I mean, to hard rot gas, if you want, with charges. So imagine you have three particles which collide, but they carry a charge. They carry a charge plus or minus, and the particles are impenetrable. So the plus and minus, when they collide, they have to, you know, reflect. And then you just consider the transport of the current. It's a deterministic model, right? There is no noise. This is a deterministic model. It lives on a space-time lattice. So everything happens in discrete time steps. So there are charges which are red, which are plus charges, and charges that are blue, which are minus, for example. And they can go across the line, the imaginary line. And then you look at the transfer current, and the kinematics of this transfer current is very easily understood in terms of these trajectories of this, what we call word lines of these charges. I have no time to go into that, but this is like essentially it's like a Curie-Weiss model in time, if you want. So you can find the moment generating functions analytically, which is a kind of partition sum of a mean field model of magnetism, if you want. No time to discuss the details, but what we can do is we can find explicitly the growth of the cumulants, which are growing with different exponents. Different cumulants are growing with different exponents, which again confirms these critical fluctuations. So this model, of course, is integrable, is even more, it's super integrable. For example, we can reproduce the probability distributions of the integrated current. This is in the log scale, this is the normal scale, it has this cusp at 0. And this is, of course, also interesting. I would need at least another 10-20 minutes to discuss, but I have to stop here. I want to just say that there are other, I didn't manage to put citation, I'm sorry for that, but there is very interesting follow-up works now by, again, group from United States by Sarang Gopalakrishnan and Roman Vasseur, who have proposed that this should be universal distribution. We now find it in particular model analytically, but now they propose this should be universal distribution for these models which have non-abelian symmetry is not crucial here, but the crucial is that there is zero net magnetization, so that there is or half filling if you want. And then there is another interesting work recently posted by a group of Michael Knapp from Munich, again suggesting something very similar. So we are about, I guess, to see a lot of development along these lines, but I have to close. So I just show you some numerics. Well, at the end, I'll show you some exactly solvable model, but the point is we have now conjectures to apply to classical and quantum deterministic models, abundance of numerical experimental evidence, but we are missing proofs. Thank you.
Okay, thank you very much. One short question, please.
Yeah, actually, two short questions. So one is, so at a certain point you were mentioning this work by Jacopo Lenardis and others, where they explain this super diffusion with you mentioned this giant quasi-particle.
Yeah.
So the first question is, what do you mean exactly by giant quasi-particle? And the second question instead is more like, do you have any physical intuition of why large deviation principles should be broken for such a...
So the first question is simple. These are just strings of,
okay.
of XXX, yeah.
Okay.
Just
okay.
Size of strings. Okay. The second question is?
The second question is if you have any physical, more physical intuition, simple intuition of why large deviation principle should not hold in this case.
It does hold, actually. No, so I mean, there is nothing wrong with large deviation principle. The problem is that there are theorems which connect. I mean, there is this large scaled cumulant generating function which you can get, which you can connect to probability distribution, integrated probability distribution of the current through the Laplace transform. So, and that thing, and that large deviation principle tells you that this probability distribution should have exponential form. Yeah, but now there's a second connection. How you get from f of lambda, the Laplace transform of this probability distribution, how you get scaled cumulants. And this needs conditions. There is a theorem by Brits and others. I mean, there are a couple of theorems in mathematical physics which are not so new, but they are well known. But in physics community, they just somehow have not penetrated. But these tell you about conditions which you have to satisfy in order to be able to say that because there are limits t to infinity, right? To get the cumulative, because the scale cumulative geometric function is t to infinity limit. You have to be able to replace the t to infinity limit by derivatives. And this is elementary and mathematical analysis, but you have to check the conditions, and this might not be true. This holds, yes, yeah, nothing wrong with that. No, yeah, of course you have to use there the appropriate power. Marton has the diffusive system, so there is t to the 1/2. It's modified in that sense. Yes, you have to use the dynamical exponent there, 1/z. He has z/2, so he has to put square root of t. We have always z equal to 1 because we have integral systems with ballistic quasi-particles. So in integrable systems, z is always 1. But still, you can have cumulants which grow with different exponents.
Okay, thank you very much.
Okay.
Unfortunately,